Let's try that again. This is take two. I was recording my pH discussion and I realized that it was a bit too confusing. I was confusing myself, so that's never a good sign. Let's try this. Now, when it comes to water discussions, we've been talking about water as this wonderful stuff. It has all these properties, heat of evaporation, specific heat expansion upon freezing. We talked about how water is a polar solvent and it's able to distinguish between polar and non-polar substances in the world. Now, apart from all of that, there's this other feature of water, which is that it tends to dissociate into hydroxide ion and hydrogen ion. We'll talk about that very shortly. Okay, I guess the reason why that's important is because it dictates the foundations for the phenomenon of pH, acidity or alkalinity, which is a really important consideration for biological systems because we tend to be adapted to living under particular circumstances, particular conditions of pH. We use buffering systems to modulate our pH to within a relatively narrow range, right? We do lots of things so that our pH levels don't fluctuate too high or too low. And we know that happens. And I guess understanding what pH is an important foundation for really getting a good feeling for what's going on with that. And that's why we're doing this. Okay. So first of all, let's go through our list. Item number one, these are two things that are item number one. We have a dissociation and an association of water molecules. And so I'm going to do this on a different board. So H2O, looking very sharp with a bond to a hydrogen. Oxygen is going to have another bond to a hydrogen. This is what it looks like, right? Yeah, and so we've got this phenomenon called dissociation coming apart. Basically, what we're saying is that water molecules are going to come apart into OH minus and plus, H plus. Okay, hydroxide ion and hydrogen ion. Excuse me. Okay, and so this dissociation is going to be taking place with the electrons basically staying on the oxygen. Okay, we know that electrons are pulled more strongly to the oxygen. It's a polar covalent bond. And so what happens when this falls apart is that the electrons that are shared between the hydrogen and the oxygen on one side, right, not both sides at the same time, but on one side, the electrons are going to be staying with the oxygen, but the hydrogen nucleus, the proton, is going to be coming off. So we end up with a H plus, which because it's just a single proton, right? And on the other side, we'll have oxygen and hydrogen, but we'll have the hydrogen atoms, electrons, staying put on the oxygen. We've got an extra electron there. So this whole thing is going to have a negative charge, right? We've got a full-on positive charge, not a delta, not a mini charge. It's the full-on protons worth of positive charge on the proton on the hydrogen ion, and a full-on electrons charge on the hydroxide ion. Okay? And that's the dissociation that takes place. It happens very rarely, okay? Because even though it does happen, water molecules are really very stable. You know, this situation on the right-hand side, yeah, the hydroxide ion is stable because it's got a complete valence shell. The hydrogen ion is actually kind of stable because the proton will associate with another water molecule to form a hydronium ion. Don't worry about that, but just take it that these two structures on the right-hand side are relatively stable, but they're not as stable as a water molecule, right? Water molecules have no charge. A hydroxide ion and a hydrogen ion have a charge imbalance, and if you were to bring a hydrogen ion and hydroxide ion together, they're going to very quickly reassociate, go back in the other direction. Okay, Dissociation is going in this direction. Association is going in the opposite direction, where hydroxide ion and hydrogen ion are coming back together to form a water molecule. Okay. But this is also going to be relatively rare for the simple reasons that we don't have that many molecules in the dissociated state, right? Most water molecules are like this, water molecules. A very, 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 very tiny proportion of water molecules are going to be in the dissociated state of hydroxide ion and hydrogen ion. Right? Okay. Now, given that we have this happening at a very rare level, it's still going to be happening on a continuous basis because we have so many water molecules, right? Association is going to be happening very easily, but we don't have very many hydroxide ions and hydrogen ions because a very tiny proportion of the water molecules are in the dissociated state. And so even though this is a very easy thing to have happen, it's a thermodynamically favorite thing to have happen for the water molecules to reform from hydroxide ion and hydrogen ion, it's going to still occur at a very rare rate because there are so few of them to begin with. Okay? And I want you to come up to the concept that if you have a forward reaction happening at the same rate as the back reaction, the reverse reaction, okay, that leads to a steady concentration, a steady proportion of water, hydrogen ion, and hydroxide ion in the solution, right? We could say that there's a concentration of hydroxide ion at any given point, right? But we also know that hydroxide ions are going to be forming water molecules as soon as they come into contact with a hydrogen ion, okay? But that doesn't mean that the concentration of hydroxide ion is going to be decreasing, because as that's happening, we have the dissociation of water to form hydroxide ion once again. The hydrogen ions are there at a certain concentration, and we know that we're constantly being converted back into water molecules as they get together with hydroxide ions. But that doesn't change the concentration of hydrogen ions because we have a continuous production of hydrogen ions through the dissociation process. Right? And so this concept of forward reaction happening at exactly the same rate as a backward reaction, okay, gives us a steady state, or we call it a dynamic equilibrium. This is going to be true in all situations where we have reactions going in both directions. It's going to happen in particular with hydroxide ions and hydrogen ions in water anytime that we've got a water-based solution, which is pretty much everything that we do in life. Okay, so let's go back to our original outline. We have first two, check and check. We have the equilibrium concept. There's a steady proportion of water molecules. As water molecules, H2O, and also in the dissociated state, the other state, this would be the associated state. The other state would be the dissociated state, which would be H plus and OH minus. Right? The proportion of molecules in the dissociated state is going to be constant. And that also means that the concentration of hydrogen ion or hydroxide ion or water molecules is going to be the same. It's going to be steady. Okay. Now, here's the next point that we need to address, which is that to say that we know that this is going to be a steady concentration in pure water. Pure water, the concentration is going to be 10, and that should be 10 raised to the -7. It's not 10 minus 7. It's just that in the Zoom text notation format, I can't make something a superscript. So 10 raised to the -7th moles per liter. Okay. Now, the reason why I was getting confused in the first take of this lecture was that I was trying to be too accurate in identifying what we mean by moles per liter. And I was putting a whole bunch of numbers on the board. Really, that's not terribly important. Okay. Don't worry about what moles per liter actually is precisely, but you do know that it's a unit of concentration. Like the strength of a solution. You know that concentrated alcohol like vodka is going to be stronger. It's going to be a greater amount of alcohol in vodka than there is in beer, right? They're both solutions of alcohol. It's that one has a higher concentration. So you could measure the concentration in terms of proof or ABV. Those are measures of concentration of alcohol. In this case, we're using a different unit. That's going to be moles per liter. Okay. Now, well, I don't really care that you understand the details of moles per liter. I do want you to focus on the value 10 raised to the minus 7th, because that's going to be directly related to the pH value. Okay. And so as we're thinking about this, I do need to spend a little bit of time on a sidebar. I call this a sidebar because it's kind of like a side discussion. I just want to remind you something from your math class, which is that negative exponents, okay, 10 raised to the minus 7th is actually a smaller number than 10 raised to the minus 6th. Okay, yeah, it's weird. 10 raised to the minus 6 is smaller than 7, but 10 raised to the minus 7th is smaller, okay, than 10 raised to the minus 6th. Why is that? Well, that's what I want you to remember from your algebra class, damn it. Right? And so 10 raised to the minus 7th means 1 over 10 to the 7th, or 1 over 10 million, right? 10 raised to the minus 6 would be 1 over 10 raised to the minus 6, so 1 over 1 million, okay? And so 1/10 millionth is smaller than 1 millionth, right? So 1/10 millionth is definitely smaller than 1 millionth, because that's what a millionth means, right? It's, this is 0.00000001, and this is 0.000001. Count that 5 zeros over here on the right, 6 zeros over on the left, right? And so this is definitely a bigger number. Good? Okay. Now here's the quiz for you. 10 raised to the minus 2 or versus 10 raised to the minus 9th. Which of these numbers is bigger? Okay. Is 10 raised to minus 2 a bigger number, smaller number, or the same as 10 raised to the minus 9th? Yeah, it's a bigger number. This is 1/100th. This is 1 billionth. And so, yeah, we're talking negative exponents. And so one of the things that is a little bit weird about the pH scale is that we're using this negative exponent, these negative exponents, to determine the pH value, the pH status of the concentration of hydrogen ions in solution, right? And so, yeah, the pH 7 has more hydrogen, sorry, let me redo that. pH 7 has fewer hydrogen ions compared to pH 6. Right? pH 2 has more hydrogen ions than pH 9. Got that? Okay. And the other thing to fill in here is that a higher concentration of hydrogen ions means more acidic. Okay. Fewer hydrogen ion concentrations, fewer H+, less acidic, or also more basic. Okay. So let's go back to our diagram here, first picture. And so, never mind about what we mean by moles per liter. Do know that it's the unit of concentration. Remind yourself that we've got powers of 10, and now we're going to be thinking about, well, what pH really represents. I've actually have it down here. Let's skip down to this point down here. The numerical value of pH corresponds to that number, that number after the minus sign, the negative exponent of 10, that will give you the molar concentration of hydrogen ions, right? Okay. So if this is a molar concentration of hydrogen ions, then that would have a pH of 7. Okay. If this is the molar concentration of hydrogen ions, 10 raised to the minus 6 moles per liter of hydrogen ions, that's going to correspond to a pH 6. pH 6 has more hydrogen ions per liter compared to pH 7, and it's going to be more by a factor of about 10, right? Okay, now down here, pH 2 is going to have a concentration of 10 raised to the minus 2nd, okay, or 1/100th of a mole per liter of hydrogen ions. And that's going to mean that we're going to be having a much greater concentration of hydrogen ions compared to pH 9, a much, much greater. 1/100th is way, way, way bigger than 10, than 1/1 billion. Right. Okay, so I hope you're not too confused by that, because what I just went through is way less confusing compared to what I was trying to do in take 1. Okay. Now let's scoot on over to the text. Where is it? Find it. Here it is. Okay. And we're looking at two sections, 2.14, which is the basic one, and 2.15 talks a little bit about coral bleaching. And so this one is basically the same as what we're talking about, but this actually gives us a nice graphic of the pH scale. And I'm sorry that I'm not able to fit the whole thing in, but you've got your book, you can look at this. And so things range in pH from very low, something that's a very strong acid, would be something like battery acid, sulfuric acid mostly. Then you've got things that are less acidic, definitely pretty strong, like lemon juice. It's really sour. Vinegar can be really sour too, but it's going to have it's not going to be as sour as lemon juice, right? Tomato juice, rainwater, we're ranging from things that are relatively acidic to things that are more alkaline or more basic. And on the alkaline side, we've got things like milk of magnesia, ammonia, household bleach, oven cleaner. Oven cleaner is lye, sodium hydroxide. And we'll be actually using that as an example a little bit later, right? And so, things range in pH from very acidic to very basic. No big surprises there, right? And so let's move back to our other discussion, other share of our whiteboard, and see where we are. Again, the pH scale ranges from 1 to 14. Any value less than 7, pH 7, corresponds to acidic solutions. Anything greater than 7 corresponds to basic solutions, okay? Moreover, it's not simply your acid or your basic. Some things are more acid or more basic, more acidic. Notice I'm using the adjective there. Okay? Acid, something is very acid. That could be an adjective. Probably very, more clear to use the adjectivity form, which would be the acidic word, or more basic or alkaline compared to a pH of 7. And so if you are at pH 8, you are alkaline, you're basic, but you're not as basic as pH 11, right? pH 11 is way more basic compared to pH 8. pH 2 is way more acidic compared to pH 4, 100-fold, right? And so, yeah, we actually see that pretty clearly in that pH scale figure that we just went through a few moments ago. I've given you the rundown on how we get from that molar concentration of hydrogen ions to the actual value of pH. We have to take the negative exponent. That basically allows you to explain why pH goes down as hydrogen ions go up. Right? Why does something that's more acid have a lower pH? Well, it's because acidity measures the hydrogen ion concentration, and as the hydrogen ion concentration goes up, things are more acid, but the pH value goes down because the negative exponent is going to become smaller. The value of the exponent is a negative, and therefore a smaller number corresponds to a greater concentration. All right, let's move into a potentially confusing thing here. We say, I've given you the idea that acidic and basic are adjectives. And they correspond to things like pH. And the pH value will tell you whether something is relatively acidic or relatively basic. Okay, it'll give you an absolute acidity or alkalinity of the solution. Okay? And these aren't the same as acids and bases. Okay? These are nouns. And so one thing that you'd be able to, should be able to do is, they're definitely related to each other. Acids are substances that make solutions more acidic, right? Acids, here we are right now, cause pH to lower, which means they're becoming more acidic. And they do so because they're either adding hydrogen ions or taking away hydroxide ions. Show you. Okay. Acid adds H+ to solution. Okay. I'll give you an example of this. Hydrochloric acid is HCl, right? It's like hydrogen chloride. Right? Now, hydrochloric acid is going to very easily come apart to make a chloride ion. It's a chloride ion and H+. In other words, when you put hydrochloric acid in water, this falls off right away. The H+ is added to the solution, the watery world, the aqueous world in which the hydrochloric acid is released. And so hydrochloric acid, you add it to water, and right away the hydrogen ion falls off. We have a chlorine. The chloride is going to be relatively stable, and we've just contributed a boatload of hydrogen ions. I mean, if you add any amount of hydrochloric acid, there's a huge number of molecules there. Every last one of those hydrochloric acid molecules is going to drop off a hydrogen ion and add it to solution. If you add hydrogen ion to solution, pH goes down because we're basically making a higher concentration of hydrogen ions, right? Another example would be acetic acid. Okay. H3 COOH. Okay. Acetic acid that's vinegar, is going to be dissociated. It's going to be losing this hydrogen ion right there. This hydrogen is going to come off as a hydrogen ion, and we're going to be seeing it turn into an acetate ion, HCCO O minus, because we've got the electrons there. In other words, it's the same molecule over here. It's acetic acid. This is acetate, and we're going to be having H plus added to solution, right? So in other words, we're adding an H plus, pH is going to go down, and that's the way that acids work, right? So an acid, a substance, a noun, is going to be something that will be making the pH drop because we're adding hydrogen ions to solution, right? Check. Bases are going to be doing the opposite. They're going to be causing the pH to increase, either because they remove hydrogen ions, or very frequently, they're going to be adding hydroxide ions. Let me show you how that works as well. So bases increase pH. Okay. One way that they could do that would be to remove hydrogen ions from solution. Okay. Ammonia. Okay. NH3 is going to become NH4 plus ammonium ion. Okay. Because this is more stable. Okay. So it's actually happier in its ammonium state than it is in the ammonia state. And it's going to do so by taking a hydrogen ion away from solution. Right? Now, because we're losing hydrogen ions from solution, that's going to make the solution less acidic. Or more basic. In other words, the pH is going to go up. That makes sense? Now, the other way that bases increase pH, this is a really common thing that happens, is they add hydroxide ion to solution. Right? So NaOH, sodium hydroxide. Also known as lye, also known as oven cleaner, also known as Drano. The chemicals drain declogger because it melts hair. So NaOH is this compound that's actually a pretty common thing to find in households. It's really dangerous. I mean, it can melt hair. It can also melt you, right? But NaOH is a strong base because it's not going to directly remove hydrogen ions from solutions, but what it will do is it will ionize, giving rise to Na+, that's our sodium ion, and a hydroxide ion. We're basically adding hydroxide ions. That has the same effect as removing hydrogen ions, because remember, OHs, if they're superabundant, makes it very difficult for a hydrogen ion to stick around. Adding hydroxide has the effect of reducing. Let's not use the word reduce. Don't like reduce, right? That's the effect of lowering hydrogen ion concentration, because hydroxides very quickly pull the hydrogen ions out of solution, right? And so that's going to have the same effect of increasing pH. Right? And so bases are substances that we add to solution and cause the pH to increase. Acids are substances that we add to solutions and cause the pH to decrease. Right? Acidic refers to, it's an adjective, it refers to solutions that tend to have a higher concentration of hydrogen ions. Bases, or basic is the adjective, sorry, basic or alkaline is the adjective that describes solutions in which the hydrogen ion concentration tends to be lower. All right. So we're done with that. Now, the question that we'll be seeing more of as we go into solution, as we go into get further into BIO110, is why does this matter to us? And your book gives you a really nice example of coral bleaching. This is not a human biology kind of thing, but it really does hit home because the world's coral reef communities are currently suffering because of the slight increase in pH of the oceans. Ocean acidification is resulting in irreparable harm to coral reefs, right? And so this chapter talks at length about how increases in the atmospheric levels of carbon dioxide are resulting in lower oceanic pH, and the consequence of that is that the microorganisms, the microalgae that are there inside of the corals are disrupted. They leave the corals and leave the animals behind with nothing to eat, or on a different diet and much weakened compared to the way that they typically are in an ocean of just even 1/10 of the pH level higher, right? It's really sensitive. I mean, just a drop of 1/10 of the pH number, like from 0.73 to 0.72, that might be enough to cause the algae that are there inside of the corals to get up and go, resulting in corals being completely without a food source. And that's just one example, right? And so, yeah, biological systems are incredibly sensitive to pH in some situations, and in other situations, the results might actually have a direct impact on humans. It's not just corals. Maybe you don't care about corals that much. Maybe you only care if it has something to do with humans. Okay, well, I've got something for you. So I've given you the coral bleaching talk. Okay, there are conditions that are, I think, nice things to talk about here, because we're talking about acids and bases. What happens when your body pH drops too low? Right? Well, you go into shock. You go into a condition called, not surprisingly, acidosis. Right? Now this is a real concern. I mean, if your pH drops too low, your proteins don't have the correct shape. They can start functioning inappropriately, and that has serious negative effects on your ability to function. Right? And so, if your blood pH were to drop much below 7.2, you would start to have serious consequences, serious health consequences. And this is a great risk for example, in situations where you have, you could induce a lower overall body pH by doing something silly like drinking a whole jug of vinegar. Okay? Don't do it, because you're going to be inducing acidosis yourself. It's going to be negative health consequences, right? So you don't want to do this. One way that this could happen kind of spontaneously, one population that's affected by acidosis are diabetics. Okay? So with diabetes, sometimes you go into this situation called ketosis, where you start metabolizing proteins, and in the process of metabolizing proteins, you end up releasing lots of acids as metabolic byproducts, and that causes your blood pH to drop down potentially very dangerously. If it drops too low, you go into acidotic shock, and you could even die from it, right? pH comes up too high. Okay. That's also serious consequences this time, right? And if your pH goes above a certain point, you go into a different kind of shock. Any guesses as to what that would be called? Why, yes, it's called alkalosis, because your body is turning into something that's more alkaline or more basic than it normally is. Okay, and so I mean, monitoring and modulating pH is a very important thing, and we actually have a system in our blood that allows us to maintain a relatively consistent pH of the blood, even though you might be binging on margaritas, which being made up of quite a bit of lime juice is going to have a negative impact on pH, right? It's going to cause pH to drop. Lime juice is acid, and if you drink a lot of acid, that's going to make your overall pH balance drop to a lower level. Okay. And so we've got these buffering systems, and this is the last thing we'll be talking about. Okay. So a buffer generally keeps things steady. Okay. And you think in terms of that concept of homeostasis. We learned about that earlier. You don't want your body temperature to go too high or too low, and so you've got this mechanism that allows you to maintain a relatively steady body temperature. You also have a mechanism to in your blood plasma, you've got a mechanism, a chemical mechanism that keeps your blood pH within a certain range. Okay. And the chemistry here is really kind of neat. It involves CO2. CO2 combines with water molecules to form carbonic acid. Okay. Carbonic acid looks like this. COOH. Right? Nope, sorry, that's wrong. I forgot an OH. What I just drew was formic acid. Carbonic acid would look like this. Right? So when you breathe, when your cells metabolize, you produce carbon dioxide. There's plenty of water in you, so carbonic acid is something that forms kind of naturally, right? Carbonic acid has this hydrogen atom, and that's the one that's going to be dissociating. So we're going to be having carbonic acid release its hydrogen ion into solution and to form bicarbonate. Right? Bicarbonate ion. And it's going to look like this. HOC, double bond O, O, the negative charge. Because it's got the electrons that are left from the hydrogen ion that is taking leave, right? So carbonic acid turns into bicarbonate ion, but it doesn't happen completely. Basically, you've got some percentage of carbonic acid still in the form of carbonic acid and some in the form of bicarbonate ion. Turns out that at pH 7.4, we have about an equal proportion of carbonic acid and bicarbonate ion. In other words, you'd have about 50-50. Might be 7.2. I'd have to double check in the textbook about this, but you have an equal proportion of carbonic acid. And basically, if you have equal amounts of carbonic acid and bicarbonate ion in your blood, okay, then you're able to respond to changes. In other words, let's say that you were to do something silly like chug a jug of balsamic vinegar, right? So you put in a whole bunch more H plus because you've drunk a whole bunch of vinegar. What happens is that we remove those hydrogen ions by having the extra hydrogen ions come attached to bicarbonate ion to form carbonic acid again. All right. In other words, we add acid, we add hydrogen ions, but we don't affect the concentration of hydrogen ions too much because bicarbonate is slurping up quite a few of them. Okay. If on the other hand, we were to do something in the opposite direction, let's say we were to do something equally silly. You know how some people are totally into alkaline water? If you were to add OH minus, because you've caught onto that silly fad, which is drink alkaline water, which is basically relatively dilute sodium hydroxide. Right? Okay, so it's basically you're drinking a dilute solution of oven cleaner when you drink alkaline water. Right? If you were to do that, that's going to cause lower hydrogen ion concentrations because the OH minus will be slurping up the hydrogen ions. And when that happens, carbonic acid will be releasing more hydrogen ions in the solution because we'll be having this go in that direction. In other words, we're taking away hydrogen ions, but it's not going to affect blood pH that much because carbonic acid is coming to the rescue and restoring the hydrogen ions that were taken away by the hydroxide ions from the alkaline water that you foolishly drank. Okay. So that's it. I do want to just add one more thing, which is that everything that we've discussed today is within the context of an aqueous world. Okay? Our whole biological cells, so basically every biochemical process, chemical reaction that occurs in living systems is occurring in the context of water. Okay? And it's only in this water context that the adding or removal of hydrogen ions makes any sense. If it wasn't water, if that wasn't water around every molecule of life, then adding a hydrogen ion wouldn't really have the same impact. You wouldn't be affecting hydrogen ions in aqueous solution because we don't have that steady state of association, dissociation that we started off with discussing at the very beginning of this lecture. Okay. Now we're going to have, maybe you've already had it, but we do have a lab on pH where we go through a practical applications of pH in laboratory experiments. And so this lecture fits along very nicely with that particular lab exercise. Okie doke, that's it.